Okay, so it's 6:05, so I guess I'll just start now. So this is going to be on general chemistry chapters 4 to 6. So these chapters actually aren't like they're not like super important other than like quite a bit of compounds and stoichiometry, but they are like foundational chapters. The chapters after this are thermodynamics and solutions and solvents. And so all of the stuff we're going to be learning today is going to be key in those chapters. So first chapter is chapter 4, compounds and stoichiometry. So you can see that it's 8%. So it's like pretty important, but the principles you learn, especially for stoichiometry, basically like apply all throughout general chemistry and also in organic chemistry as well. So it's really important to know this stuff. Okay, so firstly, just some like really basic foundations. So like I said last week, molecules are atoms held together with covalent bonds. So ionic compounds are actually called formula units. So a molecule would be something that is held together with a covalent bond. So what a covalent bond means is like this. So neither of these are metals. So these are both nonmetals. Sorry. Yeah, so these are both nonmetals. And so this is actually a polar covalent bond because it goes like that. Oh, sorry. Like this. So this is a polar covalent bond. There's also non-polar covalent bonds. This is just a review from last week, such as this one. So because these are both the same atom, they're just there's like no difference in electron density. And just as a reminder, electron density is basically pulled towards the more electronegative atom. In the last review session, we talked about electronegativity trends in the periodic table, and it increases from left to right. So fluorine is actually the most electronegative atom, and chlorine, or the chloride ion in this case, is a halogen, which is in the same group as fluorine. So it's also a highly electronegative atom. So yeah, these are polar covalent bonds. Ionic compounds are, just as a review, they're almost always a metal and a nonmetal. So for example, lithium bromide would be an ionic compound. Ionic bonds are stronger than covalent bonds, but they are actually less important for us in organic chemistry and also in general chemistry, since most of what we're going to be talking about are molecules, which are the covalent compounds. So yeah, so this is just like a reminder. So molecular or formula weight is the sum of atomic weights. So this is basically pretty self-explanatory. Like if you look at HCl again, the molecular weight would just be 1 plus 35.45. So it would be 36.45. So yeah, that's also pretty self-explanatory. Moles are also something you guys should have covered in your university lectures. So a mole is just 6.02 times 10 to the 23. This is Avogadro's number, and it's extremely useful in basically all aspects of chemistry. Because molecules are so small that we convert them to moles, or like 6.02 times 10 to the 23 atoms in order to do reactions with them or do like stoichiometry. And we'll talk more about that later. So molar mass is just the molecular weight. So it's basically grams over moles. So the molecular weight, or the molar mass, sorry, is basically just the molecular weight, but with like grams at the end. Like for example, for HCl, it would be 36.45 grams, and that's per mole. And equivalents are also pretty important. They're not like as commonly known, but they're basically just like how many moles of the thing we are interested in will 1 mole of a given compound produce. So like an example is sulfuric acid. So in sulfuric acid, 1 mole of sulfuric acid has 2 moles of hydrogen. And so usually when we talk about equivalents, we are usually talking about hydrogen or protons. So yeah, to find the amount of equivalent, you just divide the mass of the compound with the gram equivalent weight, which we will talk about here. So the equivalent weight is just the compound mass that provides 1 mole of the particle of interest. So it's just the molar mass of the compound divided by the number of particles of interest produced. So like, for example, 1 mole of sulfuric acid produces 2 moles of hydrogen. And so the gram equivalent weight, or like the number of equivalents of hydrogen, so you would need 98 grams of H2SO4 to produce 2 equivalents of hydrogen. If you have any questions, just like write them in the chat, or you can just like unmute yourself and say it too. That's also fine. A lot of this stuff like is kind of confusing. So if you need like any explanation, just like let me know. So here are some problems. So I'll just give you guys like a minute to do these. Most of these are pretty simple. We haven't really talked about the calculations yet, and we'll go over them together like in the next section. But you should have enough information to figure these out, like just based on the concepts that we learned. Okay, I guess I'll like go on to the answers now. Okay, so what is the molecular weight of nitric acid? So hydrogen is 1. So it's actually like 1.0008, but like you don't really need to like know to that detail, especially since we don't have calculators. And then nitrogen is about 14 and oxygen is about 16. So this is 1 plus 14 plus 3 times 16. So this equals, so this is about 65 atomic mass units. Okay. And then for the second question, how many moles of HCl are in 108 grams of the compound? So all you have to do here is basically just do some really, really simple stoichiometry. So we go 108 grams of HCl, and then you just multiply it with 1 mole, and then you multiply that with the molecular weight of HCl, and that was roughly 36. So this should give about 3. Actually, no. Let me see. Yeah, so it should be like about like, yeah, so it should be about 3. Sorry, I was just making sure that my calculation was right. Yeah, so it's like really simple stoichiometry. And for the MCAT, because we don't have to use calculators, you can just do like really like simple approximations. And then how many equivalents of H are in phosphoric acid? So this is just 3 because there's 3 hydrogens in phosphoric acid. And then how many grams of nitrate is needed to produce 3 equivalents of electrons? So 1 mole of nitrate produces 1 equivalent of electrons. So we need 3 moles to produce 3 equivalents. So that means that we basically just need to multiply the moles with the molar mass of nitrate. So this would just be another simple stoichiometric calculation. So the way I do stoichiometry is like this or like that. They're basically the same thing. It just makes it easier because you can like cross out the you can like cross out like the units so you know that you're getting the right unit. Okay, so nitrate has a molar mass of so nitrate has a molar mass of 62 grams. So 62 times 3 equals to 186. So 186 grams of nitrate produce 3 equivalents of electrons. All right. And the last question is actually for the next section. I don't know why I put it here. Sorry about that. But we'll go back to it. Okay. So the last question here is just on normality. The last concept here is just on normality. So normality is basically the concentration in equivalents over liters. So the difference between normality and molarity is just that molarity is like the complete moles of the compound, but normality is just like the equivalents you're measuring. So in the case of phosphoric acid, there would be 3 equivalents of hydrogen per liter. So that's basically all it is. And going back here, the molarity of a 3N solution of H3PO4, that would just be 1, because the equation for normality, or the conversion from molarity to normality is just here. So it's just 3N over 3 hydrogens, so that's just 1. Okay, yeah, so the answers are here too. Like, I don't know why I got confused, but yeah. So these are the answers here. Okay, so the second part is the law of constant composition. So this is like a pretty simple concept. It's just that pure samples of compound contains the same elements in identical ratio. So what this means is basically water is always water. So water will always have 2 hydrogens and 1 oxygen. An empirical formula is the simplest whole number ratio. So an empirical formula doesn't actually give the number of atoms that are actually in the compound. It just gives the ratio of atoms. And percent composition, and sorry, molecular formula actually gives the actual number of atoms in each element in the compound. So what this means is that the empirical formula could be something like C5H7O, but that would not be the real formula of the compound. So the molecular formula could be something like C10H14O2. So this is important because although the empirical formula is useful for ratios and for simple calculations, the molecular formula is what we actually need to do reactions. And it's especially important in organic chemistry because you can't just like simplify elements down to their smallest size, because then they're no longer the same element. So just as an example of that, like say an element has a molecular formula of CHO. So this would be CHO and, sorry, well, this would actually be like CH3O because remember, carbon always has 4 bonds. But this is not the same element as like C2H6O2, because that would be like something like that, for example. Okay, so just here are some problems on empirical and molecular formulas of a compound. These are actually not right. So this is the real question, like down here. But I'll just change it here. So this is 40. This should be 40%. That should be 7. And this should be 53. Sorry, guys, I'm not completely prepared this week. I had quite a few assignments due, but yeah, so I just like edited these slides like this morning, and I caught some things, but I didn't change like everything. So yeah, usually I work on the slides like over the week, then I just like edit them like 2 days before. But yeah. Yeah, I'm really sorry. It won't be like this usually. I was just like really busy this week. Okay, yeah. But other than that, all the numbers should be right. Okay, so I'll just give you guys like 30 more seconds and then we will go over it together. Okay, so let's go over this. Okay, so this is a bit involved. Sorry, I just have a comment. Yeah, so yeah, the MCAT is a lot of mental math, but once you practice this, you should be able to do a lot of these problems like pretty quickly. Like I think they give you a whiteboard or something. So if you have like a whiteboard, you should probably be able to figure these out like pretty quickly since they give like really easy numbers. But yeah, so let's just like go over how to do this problem. So firstly, here are the percentages. 40% carbon, 7% hydrogen, and 53% oxygen. And it has a molar mass of 180 grams. So how do we do this? Firstly, we just assume the sample is 100 grams. So this converts each percentage into grams. So that means 40 grams of carbon, 7 grams of hydrogen, and 53 grams of oxygen. And then you have to convert the grams into moles. So this is like a really important step. When I was taking chemistry, like this was something that tripped up a lot of people. Like a lot of people just assume like you can just do direct comparisons between like grams of an element. But you can't do that because like each element is like of a different size. And so you can't just like say that 7 grams of hydrogen is the same as like 7 grams of carbon, for example, because these two elements are like very different sizes and have very different masses. So this is like where moles become extremely useful because they allow us to do direct comparisons between these elements. Okay, so let's convert the grams into moles. So this is also like some really simple stoichiometry. Um, if you look at this, like one way to know that you're always like getting like the thing you need, like in this case moles, is to just like cancel out the units as you use them up. So in this case, you can just cancel out grams here and grams here, and all that's left is moles. So you know that this is 3.3 moles of carbon. And yeah, so you just keep on doing that, and you'll find that you have 3.3 moles of carbon, 7 moles of hydrogen, and 3.3 moles of oxygen. So all you have to do here is just divide all these by the smallest number of moles. So in this case, that would be 3.3, 3.3, and 3.3. So then you would get 1 here, around 2 here, and 1 here. And so you have a 1-to-1 ratio. So you can just take that ratio and convert it directly to the empirical formula, which is CH2O. And then to find the molecular formula, you are given the molar mass. So all you have to do is take the molar mass, and then all you have to do is take the molar mass and then just divide the molar mass by the molecular weight of the empirical compound. So if you actually like find the molar mass of CH2O, you'll see that it's roughly 30. In the MCAT, approximations are king. So 180 over 30, that's 6. That's extremely simple mental math. And so you can just multiply what you get by the empirical formula and you'll get C6H12O6. So if you've already studied biology, then you'll know that this is glucose. And the empirical formula is for polysaccharides or monosaccharides. So yeah, so this is an extremely important formula. You'll be using it a lot in pretty much all throughout biology and in organic chemistry too. Okay, the second part is the percent composition of hydrogen in phosphoric acid. So the molar mass of phosphoric acid is just 98 grams over moles. And then the mass of hydrogen in phosphoric acid is 3 grams over moles. Like, this is also simple. Hydrogen is has a molar mass of 1 gram. Just multiply that by 3 because there's 3 hydrogens in phosphoric acid, and you just get 3 grams over moles. And so percent composition is just 3 over 98 times 100, and you get 3.1%. So on the MCAT, if you get a question that involves percent composition, you can actually make like another approximation. You can just do 3 over 100, and you would just get 3%, which is extremely close to 3.1%. Okay. So the next part is just types of chemical reactions. So this includes combination reactions, in which 2 reactants make 1 product, decomposition reactions, in which 1 reactant basically decomposes into 2 products. And so decomposition reactions actually require some like special contexts. So this might include the addition of heat, the addition of radiation, or electrolysis. Combustion reactions are a hydrocarbon plus an oxidant, which is usually just oxygen, and the products are always carbon dioxide and H2O. So if you see like any question that says combustion, you know immediately that the products are always carbon dioxide and water, and so that's extremely helpful in answering questions. Single displacement reactions is basically just like replacing one element in a compound with another element. And then double displacement is basically switching the elements between the reactants to make the products. Neutralization is a special kind of a double displacement reaction. So in this one, you add like an acid with a base, and you get salt and water. So this is an extremely important reaction in both general and organic chemistry. We'll be talking about this reaction a lot more when we get to the acids and bases section, actually. So a very simple neutralization reaction is with hydrochloric acid with a base, and you get table salt and water. So table salt is neither an acid nor a base. So in this case, both the acids and the bases are neutralized. Okay, so here are some questions. They shouldn't take too long, so I'll just give like 30 seconds. Okay, so let's just go over it. So the formation of hydrochloric acid is a combination reaction. The decomposition of silver chloride is a decomposition reaction, and it actually involves UV light. So if you expose a solution of silver chloride to sunlight, it will dissociate into silver crystals and chlorine. If you write out the reaction for the combustion of methane, so you know that one of the reactants is oxygen and that the products are carbon dioxide and water. So all you have to do is write on methane. So methane is just CH4. We'll talk a lot more about methane and other hydrocarbons in organic chemistry. Just remember that you need to balance this reaction because there needs to be equal numbers of each atom on each side. So what are the products of the reaction between hydrobromic acid and lithium, hydroxylithium? So this is just lithium bromide salt plus water. And this was a neutralization reaction. So you just neutralized hydrobromic acid. Okay, so in balancing chemical reactions, we just need to keep in mind that there always have to be an equal number of atoms of each element plus equal charge on both sides. So equal charges will actually be a lot more in the oxidation reduction section of organic chemistry. So we'll mostly just be focusing on making sure that there's an equal number of atoms of each element in this section. The stoichiometric coefficients are the number of each compound, and you can just see that in the reaction equation. And then just as a tip, save hydrogen and oxygen for the last to balance. Because hydrogens are like, there's a lot of hydrogens usually in a lot of these compounds, and oxygen is always like a bit tricky to balance. So it's just best to save those two for last. But just as an example of like what stoichiometric coefficients are, it's just like 2 H's plus 3, I don't know, or like 2 H's plus 2 chlorines, that's 2 HCl. So these are just the stoichiometric coefficients. Okay, so here are just some balancing problems. So I'll just give like a minute to do these and then I'll show the answers. Okay, so let's just go over these really quick. So these are the answers, but let's just like do these together because sometimes balancing can be pretty tricky, like if you're not paying attention to each element. So here you can see that there's 3 chlorines here, but there's only 2 chlorines here. And so the only way that you can like balance this would be to make the number of chlorines like an even number. So all you would have to do is like put a 2 here, then you would put a 3 here and a 2 here, because you also, once you do this like that, you also just made the product have 2 iron atoms. And so you would have to put a 2 in front of the iron to make all the atoms equal. Okay, so for the second one, if you look at bromine, there are 3 bromines on the reactant side, but only 1 bromine on the product side. So you can just like put 3 in front of the hydrobromic acid. However, if you go back to the reactant side, you'll see that there's actually 2 hydrogens on the reactant side. So what you actually have to do is you would have to make this a 6, and then you would have to make this a 3. And so in that way, you have hydrogens on both sides. And then you would put a 2 here. And once you do this, you see that you actually have everything equal. So you can treat this as like a single atom because this is a polyatomic anion. So this is sulfate. And there's like a list of polyatomic anions like near the end of this section that you guys can take a look at. So yeah, you can see that there's 3 sulfates now. There's 6 hydrogens. There's 2 irons, and there's 6 bromines. And so that's how you balance that reaction. And the last one is a combustion reaction. And so here you can go to the carbons. It needs 7 carbons on the product side. So you would just put a 7 here. And then now you can see that there are actually 16 hydrogens. And so because of that, you would need to put an 8 in front of the water to get 16 hydrogens on the product side. And so now we have to count the number of oxygens. So there's 8 oxygens in water plus 14 oxygens in carbon dioxide. So that equals 22. oxygens total. So on the reactant side, you would have to put an 11 here so that there's 11 oxygens and the reaction is fully balanced. And yeah, so these are the answers like neatly written out. So it's nicer for you guys to look at if you look at these slides after. Okay, so now we'll talk about stoichiometry in general. So stoichiometry, I like to think of as the foundation of chemistry, because whatever you do, like eventually it's probably going to lead to some kind of stoichiometry. So we need to like form a good foundation like right now, so that whenever you see a stoichiometry problem, like you don't just like stare at it like, oh my God, how can I possibly get from grams to moles? So yeah, so let's just do that right now. So firstly, we already talked about stoichiometric coefficients, but these actually give like the molar ratios. So what that means is, say we go back to one of these equations here. So this also means that 2 moles of iron and 3 moles of chlorine are needed for this reaction. And also that 2 moles of, what is this, ferric chloride are formed. Yeah, so make sure you keep the stoichiometric coefficients in mind. Just as a tip, always make sure to cancel out the units while solving stoichiometric problems. This is just like a really good a strategy to check that what you're doing is right, because you should be getting like whatever you're looking for out at the end. Like that should be the only units left. The limiting reactant is what's used up in the reaction, and it limits product formation. The excess reactant is the remaining reactant. So basically what this means is that, say there's some random reaction happening. Let's say it's the formation of hydrochloric acid. So this is just HCl. So say that you have 2 moles of hydrogen and you have 1 mole of chlorine. So what that means is that because this is a 1-to-1 molar ratio, like you can see that the stoichiometric coefficients are just 1 for both of these. That means that you need 1 mole of hydrogen to react with 1 mole of chlorine. So that makes chlorine the limiting reactant because you have less of it. So there's only 1 mole of chlorine. And then hydrogen would be the excess reactant. So you have 1 mole of hydrogen left. What's really important is that when you're calculating this, always use moles. You can't make equivalencies between products in grams. So you always need to use moles here in order to compare the excess and the limiting reactant. Percent yield is the actual yield over the theoretical yield times 100. So the theoretical yield is what you're going to get like out of a stoichiometric calculation. Like in the next problem, I'll be asking you to do like a really simple stoichiometric calculation, and the answer to that will be your theoretical yield. If everything goes right in the reaction, like there's no impurities, nothing goes wrong, you use exactly the right amount of each reactant, the solvent is perfect, then you will get this amount of the product. And that will be your theoretical yield. But in a real reaction in real life, the actual yield is a lot less, because there might be like impurities in the compounds, or you might have done something wrong in the reaction. So in the end, what you get might be actually a lot less than what you would expect to get. And so we always have to do a percent yield calculation in order to see like exactly how much we actually got. Okay, so here's the problem. And I'll just give like a minute to do this one. It shouldn't be like too hard. So just like remember like the principles of stoichiometry. So use moles. And always keep track of your units. Yeah. So keep track of your units. Oh, and just a reminder, the MCAT does provide you with a periodic table. It's just like a button at the corner of your screen that you can always like look at throughout the entire exam. So they will definitely be asking questions that have to do with like molecular weights or molar masses. Okay, so let's just go over this together. Okay, so these are the answers, and to the person who commented in the chat, you were right. Iodine is the limiting reactant. So if you look at this equation, like you can see that it is a simple combination equation of copper and iodine to produce copper iodide. So this is just like call back to the last section. Okay, so the stoichiometry is written out here, but I'll just like write it out like here as well, just so we can clearly see what's actually going on. So to find the limiting reactant, we have to find the moles of each reactant in order to compare them. So 32 grams of copper, 1 mole of copper is 64 grams. So that is half a mole of copper. So just as a reminder, just like keep track of units, like you can just cross them out. Like that's what I do just to make it like really easy for myself. But of course, you don't have to. And then for iodine, so there was 25 grams of iodine, and then 127 grams is the molar mass of iodine. And then, yeah, and then we would get about 0.2 moles. And so this is a 1-to-1 molar ratio. So that means that 0.2 moles of iodine would be used to react with 0.2 moles of copper. So that makes copper the excess, and there would be 0.3 moles of copper left. And then how many grams of the product would be formed? So that is another like pretty simple stoichiometric equation. That's just 0.2 moles of iodine. And you have to use a limiting reactant here because remember, the limiting reactant is what basically controls product formation. Because if you just like think about it, you can't use copper because after you get to 0.2 moles of copper used, then there's no more iodine left to react with. And so you would basically be far overshooting the actual yield of the reaction if you try to use copper in the stoichiometry for this reaction. So you would use iodine, the limiting reactant, and then you would go on to 1 mole of iodine. And so this is another 1-to-1 ratio with the product. So this would be 1 mole of product as well. And then 1 mole of the product would be 190 grams. And so if you just like cross this out like that, you will find 38 grams of copper should be formed. And that's the theoretical yield. So if everything goes perfect in the reaction, that's what you expect to get. However, in real life, you got 10 grams because you might have messed something up, or because like there might be some impurities like in your reaction. So all you have to do to get the percent yield would be to do the experimental value, which is 10, over the theoretical yield, which is 38, and you would get 26%. So on the MCAT, like they probably give you like some rounder numbers, like 40, for example. So that would just be like, yeah, so that would just be like 25%. But even for this, you can just make an approximation of 38 to 40 and you would get 25%. So that's pretty close to 26. But yeah, that's like pretty simple stoichiometry. Like this is the foundation of stoichiometry, and as long as you keep track of your units, you should always be able to like do stoichiometry. No matter like what kind of question you get, just like make a list of each of the units in the problem that you get, and then like find out like what you need to get to, and then you can just like make a stoichiometric path to get from the beginning to the end. And by doing that, you basically should be able to solve any stoichiometric problem. Like this is just like basic problem solving. Like you just have to get from point A to like point B. And by doing this, by like canceling out units, you should always be able to get there. Okay, so most of the stuff about ions was actually just like basic nomenclature. Like basically all you could do here is memorize this stuff. So I mean, if there's like more than one positive ion, like a cation is a positive ion, then you could just like write the element name with a Roman numeral charge. Like iron 2 plus would just be written as iron with Roman numerals 2. And same thing for iron 3 plus. However, there's like a more outdated method of doing this. So there's like the element name adding like an us for less charge and an ik for more charge. So this would mean that iron 2 plus would become ferrous and iron 3 plus would become ferric. However, like us and ik aren't related to 2 and 3. Like what they're related to is just less charge versus more charge. So like an example of what I mean is that copper 1 or like copper plus is cuprous and copper 2 is cupric. So just like less charge is us, more charge is ik. So for monoatomic anions, all you have to do is drop the name ending and add an "ide" at the end. So the bromine anion just becomes bromide. The oxygen anion becomes oxide. Just as a reminder here, all of the halogens are always going to be -1. Halogens are always -1. The oxygen group is always -2, and so forth. The next one are the oxyanions, and these are polyatomic anions that include oxygen. So if there's less oxygen, it's ite. If there's more oxygen, it's ate. So we already had some problems involving nitrite and nitrate. So yeah, so NO2 minus would be nitrite, and NO3 2 minus would be nitrate. And also like these should be superscripts. I just got lazy here, but this should be like NO3 2 minus. Yeah. And then the extended oxyanions are just like when there's even less oxygen, you put a hypo in front. And if there's even more oxygen, then you put a per in front. And so this is just hypochlorite to chlorite to chlorate to perchlorate. And each of these just has one more oxygen each time. And then the hydrogen or like the proton anions, like if there's a proton in it, then you just add like a hydrogen in front of the ion's name. And then the older method is if there's like a hydrogen, then you would just like put a bi in front of the name. So an example would be hydrogen carbonate or bicarbonate and dihydrogen phosphate. So hydrogen carbonate in particular is very important because it is part of our bicarbonate buffer system in our blood. And if you have if you've already finished the biology or the biochemistry book, you'll have learned a lot about the bicarbonate buffer system. For the charges, we talked about the charges at the last review session, but all you have to do is basically look at the periodic table for the representative elements. So like in group 1, those are the alkali metals. They include like lithium and sodium. And so you would add like a +1 charge. The alkaline earth metals like magnesium and calcium would be a +2 charge. If you go to the other side of the periodic table, then the halogens would be -1 charge. Oxygen would be -2 charge, and so forth. And so you can justify this by thinking of the octet rule. So a halogen is extremely close to an octet. It's right next to the noble gases, which have like a perfect octet. And so all you would have to do to make that octet is add an extra electron. And that's why halogens are always desperate for that extra electron. Yeah. Oh yeah, so electrolytes are solutes that allow solutions to carry currents. And so these are actually like more important for ionic compounds. So ionic compounds in a solid state do not conduct electricity, because like a solid has atoms that like barely move. So because the atoms can like barely move, they can't conduct electricity. However, if you put those ionic compounds into a solute, that enables them to basically dissociate, and they basically become free ions, then they can carry currents. And so electrolytes operate along a spectrum. A strong electrolyte dissociates completely into anions, ions. So, you know, like say, like table salt, NaCl. So that dissociates completely into sodium and chlorine. And so that would be a strong electrolyte. Weak electrolytes don't dissociate completely. Oh yeah, and transition metals. So transition metals have numerous charge states because they also have their d orbital free to accept charges into. And so because of that, they have like numerous charges. Like one example would be like chromium, for example. You can have chromium 2+, 3+, 4+. So yeah, and so forth. But you generally don't need to memorize these. Like you would be given like charges or the compounds. Okay, and here's just a list of ions. So you can't really do much except memorize these, but a lot of these are like pretty important, like polyatomic ions and anions mostly. So of these, I would definitely say like know this one. This is the ammonium ion. You might know it better as ammonia, but yeah, that one's pretty important to know. Cyanide isn't super important, but like all of these, this is hypochlorite, chlorite, chlorate, perchlorate, and this is just like an example of the extended oxyanions. 100% know the hydroxide ion, know the nitrate and the nitrite. Permanganate isn't super important. Definitely know hydrogen carbonate. No carbonate. This one's pretty important. Yeah, but those are mainly the most important ones. The phosphate ions aren't super important, but if you have time, just like try to memorize them too. Okay, so now we'll just move on to chemical kinetics. And this is chapter 5. And yeah, I'm using Notability to the person in the chat. Yeah, last time I tried to like do it on my computer and I couldn't like write anything. So I thought that this might be like a better option. Okay, so there's like 2 asterisks here. That basically means that this is like a high yield chapter. So this is super important on the MCAT. So firstly, Gibbs free energy change. So delta G. So delta G you'll see a lot. It basically determines if a reaction is spontaneous or non-spontaneous. If it's spontaneous, the delta G will be negative. If it's non-spontaneous, it will be positive. We'll find out why. It's either positive or negative on the next slide. So in the body, we have enzymes that are needed to act as biological catalysts to increase the reaction rate. And so the reason why these are important is because a lot of these reactions happen like extremely slowly. So like they're so slow, they might like take a whole lifetime to get through. And we need these reactions like to happen in our body like fast, 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 because we need to stay alive. And so our body produces enzymes that act as catalysts. If you don't know what catalysts are basically just like compounds or like structures that are involved in the reaction, that they so they are involved in the reaction mechanism. However, in the end, they actually aren't used up by the reaction. So you won't see a catalyst like in the reaction equation. Like for example, I'll just use like HCl again. So I actually don't think the formation of HCl needs a catalyst, but like say it did, right? Say it needed a catalyst. So say like a base was a catalyst, and this would not work at all, but like just pretend it was. Then like the base would be like used during the reaction, but you wouldn't see it in the products because it was just reformed again. Okay, so the reaction mechanism is just the steps needed for a reaction to occur. And it's like more than the formula. So like, I guess one example could be this addition of a compound onto benzene. Like for example, we have benzene here. And then we want to add, say, an OH group. You can't just like add an OH group. Like there's a bunch of stuff that needs to happen. It's like an extremely complicated reaction. I actually don't think it's even covered on the MCAT. But for example, like one thing that would need to be happen would be the formation of like a benzyne ion. And then a lot of like really complicated stuff happens, and then you get all the way over here. But you don't see any of this in like the reaction formula. And so reaction mechanisms aren't talked about a lot, like in general chemistry. Like it's basically the bread and butter of organic chemistry though. So just like be aware that a reaction mechanism is like not just this. It's like a whole bunch of steps that happen. Then you get all the way here. Okay, so the rate determining step is the slowest step. So the slowest step is the step that takes the longest to happen. Like say in this reaction, to go from benzene to a benzene with a hydroxide added to it, the formation of the benzene, this thing, that would be the rate determining step because it takes the longest to happen. And the rate determining step basically just like determines how fast product formation is. The collision theory of chemical kinetics is that the rate of reaction is proportional to the number of collisions per second between reacting molecules. So like this should make sense. So if you think about like a reaction, like what's actually happening is like say there's like a bunch of atoms in a solution, and here's one molecule, here's another molecule, and these are like two reactants, and they have to like somehow collide in order to react. And so the faster they collide, or like the number of collisions that happen, that would determine the speed of the reaction. Yeah, because you can't just like put like two compounds into a solution and expect something to happen. Like they have to collide with each other in order to have like the product form. The effect of collisions is the minimum energy of collision, which is the activation energy, and it also requires like correct orientation. So say like this is one reactant, and then this is another reactant. So they would have to collide in this orientation to react. If they collide like that, like they can't react. So they have to collide in the correct orientation. So orientation is talked about a lot more again in organic chemistry. So we don't talk about it a lot in this, in general chemistry. So in general chemistry, mostly talk about the activation energy. So the activation energy is just like, there has to be like a minimum energy of the collision. Like say like two molecules collide, but they don't have enough energy. Like nothing is going to happen. But if they have enough energy, then like they're going to form the product. Reaction rate, this is the equation, is just Z times F. So Z is the total collisions per second, and F is the fraction of collisions that are effective. So this is pretty intuitive because say there's like 100 collisions that happen, but only like 25% reach the minimum threshold in the correct orientation. Sorry. So that would just be like 25 would be the reaction rate in that case. However, we don't actually use this equation a lot because it's really hard to know like how many collisions there actually are a second. Like it's very difficult to experimentally determine. So we actually talk about reaction rate in a different way, and we will talk about that in the next section. But first, we will talk about the Arrhenius equation. So absolutely know this equation. This is a very important equation. It is like key to chemical kinetics. But don't worry, you won't have to actually do this equation because you definitely need a calculator for that really big exponent. But you just need to like know the relationships here. And the relationships are kind of tricky, so we'll just like go through this. Okay, so here's a problem at the end. So we haven't really talked about the relationships yet. So I'll just give like 30 seconds to see like if someone does know like how the rate constant changes, because you should be able to figure it out from the reaction, but it is a bit tricky. So we'll talk about it together though. Okay, so let's talk about this. So all you really need to know in this reaction is, sorry, in this equation is the change in temperature. Like all of these other variables don't even matter. So let's just set all of them to 1. So let's set K, which is the rate constant. K will become very important in the next section. Let's set K equal to 1. Let's set A equal to 1. And so E is actually a number. Like if you don't know, E is the natural number or something, and it's like pi. It like never ends. So it's like 2.7, but all that really matters is the 2.7. So yeah, and so let's just set the activation energy equal to 1, and then let's just put in the temperature. So we go from 100 versus 200. And so of these, like intuitively, right, you would think that, so intuitively, like if you look at this, you'd be like, okay, if the temperature is increased from 100 to 200, that's like a bigger fraction, right? So doesn't that mean that because it's a bigger fraction, it actually gets smaller? So like the reaction rate would decrease. But like you don't think of it, you shouldn't like think of it like that, because remember the negative, right? The negative is incredibly important. And in this case, the smaller the fraction gets, the less negative the equation becomes, or the less negative the rate constant becomes. And so here's like a neat version of this. So yeah, so the explanation is here. So basically increasing the temperature makes the fraction smaller, which means that the whole equation is actually less negative. So therefore increasing the temperature actually increases the reaction rate. And this is constant across all reactions basically. If you increase the temperature, you're going to make the reaction faster. And so in organic chemistry, that you'll see that several of the reactions they talk about have to happen in high heat, because if the reaction has higher heat, then that means like the molecules are moving faster. And so that's because temperature is actually a measure of the kinetic energy of the molecules. And so if you increase the temperature, you increase the molecule's kinetic energy. And if you increase the molecule's kinetic energy, that means they're moving faster. And if they're moving faster, that means there's more collisions happening. And if there's more collisions happening, that means that the rate constant of the reaction increases. So yeah, so when you look at this equation, just always bear in mind that there's a negative in the exponent. And because of that negative, what you intuitively think is actually the opposite. So if you increase the activation energy, for example, that means that the reaction rate would actually slow down because you're making the fraction bigger, and therefore you're making the equation more negative. Because you're making it more negative, that means the reaction is slowed down. Yeah. So yeah, just remember the relationships here, and just as a rule of thumb, remember that if temperature increases, the reaction rate also increases. Okay. So chemical kinetics, one last thing is the transition state theory. So this just means that effective collisions form transition states, which eventually dissociate into products. And so this is like part of what I was talking about. Equations aren't just like the formula. There's like a bunch of steps that happen until you get to the formula. And those steps include transition states. So the transition states are like, happen for like milliseconds. So they're theoretical. Like we expect this to happen, but you're never going to like actually collect this. Like if you do a reaction, you'll never like collect a product that's a transition state because they happen for like nanoseconds or milliseconds, if that. If you look at a reaction, if you look at a reaction progress diagram, it generally will look like this. So you start with the reactants, then the hump is the transition state, then it goes down into the products. And so remember free energy, it is important here, right there. That's the free energy change. So the free energy change is just the difference in the energy between the reactants and the products. So this is actually an exergonic reaction. And so there's a negative delta G because that means the products have less energy than the reactants. And because the products have less energy than the reactants, that means that delta G is negative. And so this is basically the explanation of why like negative equals spontaneous reaction. So spontaneous just means like it's going to happen. If you have like these two reactants here and the delta G is negative for these two reactants, then you don't need to do anything else. Like the reaction is going to happen no matter what. Okay. Yeah, so this is the activation energy here. So the activation energy is the energy needed to reach that transition state. And once you've reached that transition state, the rest of the reaction can happen. This is a reaction with only one transition state, but just know like there can be multiple transition states. Like for example, you can go like that, like for your reaction, except like it should be probably more like that. And then each transition state, this would be 1, 2, 3. The transition state that's the biggest would be the rate determining step. So in this particular reaction with 3 transition states, the one that leads to the formation of transition state 2, that would be the rate determining step right there. Okay. So really quickly, draw out the reaction progress diagram for an endergonic reaction. Remember that this diagram was for an exergonic reaction. So exergonic means that there's a negative delta G. So therefore an endergonic would mean there's a positive delta G. So just like draw out like really roughly what that would look like. And also draw out what would happen if a catalyst was added to the reaction mixture. So remember that a catalyst speeds up the rate of the reaction. And just like think about why it would do that, how it would do that. Because remember, like a catalyst doesn't affect the product. A catalyst is not involved in the product. So just like look at this diagram and think about where exactly the catalyst would affect the reaction. Okay, so I had one answer that it affects at the reactant side, not quite, but you're close. So yeah, it decreases the catalyst decreases the activation energy. And because it decreases the activation energy, that means a lot more molecules can reach that energy that makes it an effective collision. So if you remember, like when we talked about the collision theory, so what matters is that enough molecules reach the threshold of energy, and also we're properly oriented. And so if you decrease the barrier, the activation energy barrier, that means more and more molecules can react. That means more molecules can react, basically. And for endergonic reactions, because there's a positive delta G, that means the products have to be at a higher energy than the reactants. And so that's why these reactions are considered non-spontaneous. Sorry about that. Yeah. So they're considered non-spontaneous because they don't happen. Like if you put these two reactants, like you put reactant A plus B next to each other, they wouldn't react. But you would need to do something special. Like you would need to add a catalyst, or you would need to add like heat or UV light or something that pushes the reaction towards the products. So yeah, that is the energy diagram. This diagram is pretty intuitive, but just make sure like you know it, like just generally, because you might see something like this on the MCAT. Okay, so yeah, so this is basically what I just said. So these are just other things that affect reaction rates. So reaction concentrations affect reaction rates. So if you increase the number of reactants, there's more collisions, and so you would make more product. If you increase the temperature, like I was saying, like that means there's going to be a faster rate. An approximation is that if you increase the temperature by 10 degrees, you double the reaction rate. However, you have to take this with a caveat, because in the body, enzymes can actually denature at a certain temperature. So remember that enzymes are proteins, right? So like at a certain temperature, they're just going to fall apart. Like it's the same with humans. Like if you set a human on fire, like they're going to die, right? It's kind of the same thing with enzymes. Like say, you know, like I live in Toronto. It's like really cold here. If I go down to like LA, then I am happier. And so I would work more, for example. But if you set me on fire, there's like lots of wildfires in California, then I would just die. So it's the same thing with enzymes. If you like increase the temperature too much, that enzyme just like dies basically. Yeah, so another thing that matters is the medium. So the medium depends on the reactant molecules. What like prefers like means is that in terms of polarity. So for example, like polar molecules, like polar solvents. So solvents are just the things that the molecules would dissolve in. Like say, for example, you wanted to react a base with something. And so you would put that base in a water solution. So water is also polar, because if you draw out this, you can see that the water has two polar covalent bonds. If you draw out that, yeah, that is also a polar covalent bond. So polar likes polar, non-polar likes non-polar. And then catalysts increase the rate by decreasing the activation energy, and they don't show up in the reaction equation. Homogeneous catalysts are in the same phase. Like say a catalyst, say like the mixture is in aqueous phase, so the catalyst would also be aqueous, versus heterogeneous, the mixture would be aqueous, but the catalyst would be a solid. So that's all that means. Okay, so reaction rates. So these are pretty important. I have had questions like this on like practice exams I've taken. So I would say like know this. Yeah, so the rate law is based on experimental data. So what that means is that in a forward irreversible reaction, all the reactants would be transformed into products. So what that means is that you can make a rate formula that is basically this. So all this means is that the rate of the reactant becoming used up is the same as the rate of the products being formed. So you can see there's a negative here. That just means that they're being used up. However, normally we can't just use this because we don't actually like know these changes well, because just the nature of an experiment, like it's really hard to like know how much exactly these things are changing. So what we do is use the rate law. So this is the rate law. So it's just rate equals a rate constant times the concentration of reactant A to an exponent times the concentration of reactant B to an exponent. So the exponents are the reaction orders with respect to each reactant. So reaction orders are like important. We'll do like more of a discussion on them within the next few slides. But just like to find the reaction rate, you would have to use experimental data. You can't just find it from a formula because, yeah, so because, remember, like a reaction doesn't always like fully happen, right? Like there might be impurities, for example, in like the reaction. Like remember we were talking about percent yield, actual over theoretical, and we actually got like a pretty small actual yield. So you would have to use like the experimental data to find like the rate law. So rate, the units of rate should be in molarity over seconds. So that's just important to know for when you're doing stoichiometry or if you're doing like calculations. If you're trying to find rate, it should be in moles over seconds. Okay. So the rate is just how quickly the reaction gets to equilibrium. And we'll talk more about equilibrium in the next chapter. Okay, so here's a problem. So find the rate law given the following data. So I'll just give like a really short amount of time since I haven't like gone over this. And it's actually a pretty involved process to find the rate law, but it is important to know how to do this. So we'll just like go over it together. But firstly, I'll just give like a few seconds to people who do know how to do this. So just as some extra practice. Okay, so let's just like go over this. So first, you need to find like each exponent. Like remember what the rate law is. It's this, right? Let me see if I can just like copy this. Okay, so yeah, so this is the rate law. And firstly, what we need to do is find these exponents. So firstly, we need to find x. And so x is the exponent for the concentration of A. So what we can do here is that we need to find like 2 trials out of the 4 trials we are given in which A changes but B stays the same. So right now we can pick trials 1 and 3. So you can see that A changes from 1 to 2 but B stays at 1. And then the rate changes from 2 to 4. And so we can see that the initial rate increases from 2 to 4. So 2 times 2, that's 4. So it increases by a factor of 2. And the concentration of A increases from 1 to 2. That's also by a factor of 2. And so all you have to do, because everything else is constant, you can just like cross everything out. Like you don't need to use like B anymore here, right? So, and you don't need to use that rate constant because it's like this is also the same. So you would just do like the change in the rate equals the change in the concentration. So the change in the rate was 2 and the change in the concentration was also 2. And you would just think like, how would you get from 2 to 2 with an exponent? And the answer is if the exponent equals to 1, then 2 stays 2. And so that's a first order reaction basically. So finding y is the exact same process. So you can take, yeah, so you can just like pick 2 trials in which A is constant, but B changes. So you can do these 2. And you can see that A stays 2, but B goes from 1 to 4. And the rate changes from 4 to 16. So both of these are factors of 4. And so this reaction is also first order. And so you can just, then after that, after you're done, you can just plug in the data from any of these trials. Like say you wanted to use like trial 1 because it's like pretty easy. Then all you would have to do is plug in the numbers here to find the rate constant. So the rate would be 2, concentration of A is 1, it's to an exponent of 1, then both of them are to 1, and so you would see that the rate constant equals to 2, and then the full rate equation is just 2A times B, and that's your full rate equation. And this overall reaction is second order because you just add them together, like you add the exponents together, so this reaction is second order. Okay, so these are reaction orders. So there's actually a lot to talk about in regards to reaction orders, but all of it can be summarized in this like diagram. I also recommend like going here, like if you like want more practice or like if you need like more help, it's like a really, really great online textbook. Okay, so 0th order. Yes? Okay, sorry, I thought someone just said something. Yeah, okay. So, yeah, so 0th order basically means that the reactants do not matter in this reaction. Like think about what 0th order means, right? That just means like an exponent of 0. So say the rate would be like A to 0, B to 0, and there would be the rate constant there. But like 0, like an exponent of 0 just means like 1, right? So that just means the rate is K. Like all it is the rate constant. So yeah, so the concentration of the reactants like don't matter in the reaction. All you need to do is like put in the reactants and then it will happen. Like as long as there's like some amount of reactant like in the reaction mixture. In first order reactions, only one reactant matters. So like for example, B would be to the it would be like B to the 0, A to the 1. And so here you can see A is all that matters. And then for this one, I guess, like it can either be like A and B both matter, or it can be like A is to the second order. Like you would find that here, right? So like say, for example, it would be like say you did this whole thing, but the answer instead of 1 was 2. So yeah, so that would be a second order reaction then. And then B still wouldn't matter. But like more commonly on the MCAT, like you'll see that both reactants matter, and that's a second order reaction. And so Kaplan said that we'll see very few higher order reactions than that on the MCAT. So we don't really need to talk about them. But yeah, so just remember these graphs. So 0th order is linear, and both first and second order are exponential graphs. And so you can actually make the exponential graphs linear by either taking the natural log. So like here, you can take the natural log and make it linear, and for this you can take the reciprocal and make the graph linear. And so you might actually like get these graphs on the MCAT. So just like kind of know the difference between them. All you really need to like know from these graphs is that be able to recognize that natural log means first order and reciprocal means second order. And if there's like none of those things, it's a 0th order. And yeah, so here they just like give like an example of relative rates versus concentration. And then half-life is just like the time it takes for half of that reactant to be used, for half of that reactant to decay. So yeah, so there's a lot more about radioactive decay, like I think in the last few chapters of this textbook. So just know that a half-life is just like the time it takes for 50% of the reactant to decay. And so there's actually different half-life equations like for each reaction order. There's a derivation for these, but actually like it's a lot easier like if you just like look at the relationships. Like here you can just see that this is just like the concentration over 2K. And then first order is just 0.693. Like you don't need to know the 693, just know that it's like something over K. And then the next one is just like 1 over K times the reactant concentration. So honestly, like I just like memorize these, but like you don't need to. Like if you're like super smart, you can always derive these, but it's just easier to just like know the relationships here versus trying to derive them. Yeah, and so the units of K are also pretty important. Like if you do like the full rate equation, then you'll find that the units of K are either like molarity over S, 1 over S, or 1 over molarity times S. So the units aren't like, so you don't need to memorize like the units, but like if you get a question and they have like different units and you know that the reaction is 0th, 1st, or 2nd order, like you might be able to just like eliminate some options just based on the units of K. So yeah, like as long as you have the rate law, like, and you've tracked the units, then you can always like find the units of K, or you can just memorize them. So either way is fine. Okay, so chapter 6 is equilibrium. So equilibrium, as you can see, is not a very important chapter at all. It's only like 3%, but it does provide like an important foundation for the next chapter, which is thermodynamics. And thermodynamics is an exceptionally important chapter. So we will just go over equilibrium. It's not like a really long chapter, and a lot of it is pretty intuitive. Okay, so for the rate law, we thought that the reactions are irreversible, and irreversible means that they go to like completion and you can't get the reactants back from the product. However, in reality, the majority of reactions are actually like reversible, and so they can go forward or backward depending on features of like the environment or like how much of the reactant or product there is. And so the reactions happen not to completion, but they go on to like dynamic equilibrium. So dynamic equilibrium is like forward and reverse reactions happening at the same rate. So you get the same rate of like product formation and reactant formation, or like product decomposition and reactant decomposition. And so equilibrium is when entropy or energy distribution is at a maximum and the delta G is at a minimum. So the delta G being at a minimum should make sense because when a reaction happens, there's like a pretty dramatic change in the free energy, right? But when the reaction is at dynamic equilibrium, that means like the rates of the forward and the reverse reaction are similar. So like you're not getting much more reactant or product forming. And so that means like that's a stable state. And stable always means very little energy change. And so, yeah, so it's like a stable state basically. So this is the derivation of like K concentration. So, and K concentration will usually equal K equilibrium, and K equilibrium is the equilibrium constant. Before we had the rate constant, now we have the equilibrium constant. Thankfully, the equilibrium constant is a lot easier to get than the rate constant because it's literally just reactants, or sorry, products over reactants. So I think this is actually backwards. I'll like correct it, but the actual equation is like right here. It's like right here. Yeah, it's like right there. Yeah, so it's just products over reactants. So the law of mass action states that at equilibrium, at a certain temperature, there's a ratio of K equilibrium of products over reactants. So that's just what I was saying here. And on the MCAT, the equilibrium constant will equal like the concentration constant Kc like almost all of the time. So this is like a valid equation that we can use. And unlike the rate law, we can actually just use the stoichiometric coefficients to do the equilibrium constant. So yeah, so you can just like look at this equation. It's pretty self-explanatory. But one thing to keep in mind is that concentrations of pure solids and liquids are not included in this equation. So what that means is that like H2O, water is not included. What's a good solid? Say you had like solid sodium for some reason. That would also not be included. So only aqueous phases and gas phases are included. And the reason is because the majority of reactions happen in like aqueous or gas phases because there's particles like constantly moving in these phases. And because like a solid is like so packed tight that the components of the solid like don't really react with each other. So that's why you need like either an aqueous or a gaseous phase for the reaction to be at equilibrium. Like obviously like the solid and liquids can be included in the reaction, but they're not included in equilibrium, in the equilibrium equation. So the larger the equilibrium is, the farther toward the product it is. Like this should make sense because if the equilibrium is larger, that means like the products, which are in the numerator, are like much higher. So yeah, so that just means that the equilibrium is farther toward the product. So at equilibrium, there will be like lots and lots of products forming and very little reactants forming. So the reverse reaction will like rarely happen. If you want to find the equilibrium constant for the reverse reaction, all you have to do is do the reciprocal. So 1 over the equilibrium constant, and that is the reverse reaction. For the multiple step reactions, all you have to do is multiply k's of the forward reactions and divide by the k's, or like the rate constants of the reverse reactions. And that should equal the equilibrium constant. So this would be pretty useful to know, actually, that the rates equal just like product over reactants. Okay, so here is a problem. Yeah, so you should be able to figure this out based on this stuff. So I'll just give like a minute to do this. Okay, so let's just go over this. Okay, so we had 3 moles of N2O4 placed in a 0.5 liter container, and that is allowed to reach equilibrium according to the following reaction. N2O4 goes to 2 of NO2. So what is the equilibrium concentration of NO2 given a K equilibrium of 6 times 10 to the 6? So all we have to do first is firstly like do the general equation here, which is just NO2 to the stoichiometric coefficient, which is 2, over the reactant, which is N2O4. So first, we have to find the molarity of N2O4. And so we get that because we know that molarity is just moles over liters. And so we have 3 moles over 0.5 liters. So the molarity is 6. And so all we have to do is plug this into that equation. However, this does require some trickiness because first we just use X for the amount of N2O4 that reacts and 2X for the amount of NO2, because remember, looking at the reaction, 1 mole of N2O4 is 2 moles of NO2. And so, yeah. So 6 minus X is the amount of reactant left when the reaction goes to equilibrium. Because remember, X is the amount that reacts. But there's only like a certain amount that reacts, and there's some that's left over. So what's left over is 6 minus X. And so we can just use 6 times 10 to the negative 6, which is given for equilibrium, and you plug that into the reaction. We can actually do like an approximation here because this K is so very small that 6 minus x is probably very, very small, so we can just estimate the amount of reactant left to be 6. And the reason for this is because remember that K, when it's like very big, is very favored toward the products. But in this case, the K is very small. So the reaction is favored toward the reactants. So not many of the reactants actually, so not many products are formed, and the majority of reactants are still left. And so for that reason, we can just approximate K to be 6. And so all we have to do is plug that in. And then we get, for x, we get 3 times 10 to the negative 3 into 204. This should not be produced. This should be the amount that was reacted. And after that, we can just multiply that by 2 to get the amount of NO2, which is the product. The last part of this section is just the reaction quotient. So reaction quotient is the exact same thing as the equilibrium constant, except that you can do this from any point in the reaction. Like it's not at equilibrium. So what the reaction quotient is showing is how far the reaction is from equilibrium. So if it's like significantly lower than the equilibrium constant, that means like there's more reactants than product. So therefore the reaction is favored in the forward direction. So you want to make more products. If it equals the equilibrium constant, that means it's at equilibrium. And if it is significantly greater than the equilibrium constant, that means that there's more products like currently in the reaction mixture. And so the reverse reaction to form more reactants is favored. And so just as a reminder again, pure liquids and solids are not included in equilibrium calculations. Okay, so we're almost done. The last part is Le Chatelier's principle. If stress is applied to the system and it's no longer in equilibrium, the system shifts to relieve the stress. So basically the system always wants to be in equilibrium because it's the lowest energy state. So it's the most stable there. So for example, if you change the concentration or the pressure or the volume so that the reaction quotient is no longer equal to equilibrium, the system reacts in the direction against the added species. Like say you add in more reactants, then the reaction would start to favor the products more because you want to use up the reactants and have more products. And so you have that equal ratio at equilibrium again. You can also change pressure and volume, but just remember that these only affect gaseous species. And so the reason they only affect gaseous species is because if you just think about like a solid or a liquid, if you try to compress a solid or a liquid, then like the volume doesn't change. Like that's one of the characteristics of liquids and solids. Like the volume doesn't change. Like you can do this like right now. Like if you have your phone next to you, just like pick it up and try to squeeze it. You can't like change the volume, right? No matter how much pressure you add. And so that's why pressure and volume changes only affect gaseous species. And so we will have, I think, a problem about this, but if not, we will, yeah. Yes, we do have a problem about this. Okay. And then the bicarbonate buffer system is an important example of Le Chatelier's principle. So the bicarbonate buffer system in our blood makes sure that we're not being poisoned, basically, with carbon dioxide. And so what that means is that if there is more carbon dioxide here, that means that the reaction favors the production of bicarbonate. But if there is too much bicarbonate, the reaction goes this way and favors, or it goes this way and favors the production of protons in the bicarbonate ion, or carbon dioxide and water. So that's just like an important buffer system in our blood. You'll learn about this a lot more in biochemistry. And so here is a problem. I'll just give like 30 seconds to do this. Yes, you are right. So like as I was saying before, pressure, the increase in pressure only affects gaseous species. So what that means is that we just have to look at the amount of gas on each side. So on the reactant side, there's 3 moles of gas. You can see it here and here. On the product side, there's 4 moles of gas right here. And so that's why if the pressure is increased, then you want to make more gas. So you go this way. And the reason you want to make more gas is because if you increase the pressure, like you're basically compressing the molecules more. So you're making them go closer together. Sorry, you want to make less gas. I'm so sorry. Yeah, you're basically making the molecules go closer together. So if you do the reaction to the side that has less molecules of gas, then there will be less molecules that are all crowded together. And so because they want to be as far apart from each other as possible. Okay. And so these are just temperature changes that affect Le Chatelier's rule. Temperature changes actually directly affect the equilibrium constant. And so the reaction must move in a way that restores equilibrium. And so temperature changes like don't directly affect like the reactants or the products, they directly affect the equilibrium constant. So what that means is that like, just think of what temperature changes do. So if you increase the temperature, then you're making the molecules move faster. And you're making all the molecules move faster, like not just products, not just reactants. Because they're all moving faster, you have to change the equilibrium constant. And therefore, the entire reaction must change so that you can restore equilibrium at that increased equilibrium constant, for example. And so the way you can do these calculations is that if the reaction is exothermic, you treat the heat as a product. If it's endothermic, you treat heat as a reactant. So you can think of heat as energy, right? So heat is a form of energy. So in an exothermic reaction, you know that energy is released. And so that's why you can treat heat as a product. In an endothermic reaction, you actually have to add heat. So you add energy, so the reaction even happens. And that's why you treat it as a reactant. Okay, so here's a problem. It should not take long, so I'll just like take it up after 10 seconds. Okay, so heat is added, so you know that the reaction is therefore endothermic. And so you treat the heat as a reactant. And because there's an extra reactant there, the equilibrium shifts to favor the formation of the product. And so once again, this should make sense because you need energy to be added in an endothermic reaction so the reaction progresses toward the products. Okay, so we're finally done. We covered 3 entire chapters. So hopefully none of this was like too confusing. But there's a ton of really cool, but there's like a ton of like videos like from Khan Academy or from AK lectures that you can watch in order to make this clearer. There's also like tons of practice problems. Like if you have the Kaplan books or you have online versions of the Kaplan books, you can definitely like take a look at those. But ideally, you shouldn't do like too many of those because all of the Kaplan problems actually require the use of a calculator, which isn't like the best for the MCAT. So definitely like try to use like UWorld or Khan Academy or like the AAMC materials to practice. So you can get into the MCAT mindset. Okay, we're done. 3 chapters. So the next session we'll have the next 2 or 3 chapters. Okay. Thanks so much. I'll just stop the recording now.